Hello, we are Group 1 of SEP 4. Here is the presentation video of our Smart Greenhouse project. IoT group will start first.
Hi, so today I'm gonna be talking about the tasks which we have made in our IoT project. And so basically we can start with the first method, which is the free memory available. So this just basically shows how many memory we have available in our system. So and all this, the principle of this is it just takes all the free memory available, fills it with bytes, and then afterwards it frees it, and then we know the size of the free memory. And then if we go to the main method, we have all this stuff from the template which we had. Then we're initializing the shared data class, and we're initializing it. Then afterwards we have to initialize the drivers, which are temperature, CO2, light, and then we have to initialize the LoRa. To be mentioned that all of these tasks should go synchronous, so all of them are just initialized one by one. So basically the temperature should go after the temperature should go CO2, light, and LoRa, and so on. And yeah, and after that it makes a new task, which is to initialize the system. And initializing this is the task. Just basically, again, we're getting the shared data pointer, then we're putting some delay, and then we're writing that in it starts. Then it starts the temperature humidity task, CO2 task, light task, and LoRa task. Just to mention that we're sending the pointer to the task itself so that it could use the same shared data class. If we go to humidity temperature task, for instance, first of all, we need to initialize the driver. So here it tries a number of times, and if it gets the OK return, then that means it was initialized and we can move on. If something went wrong, and we can just keep on we are just counting the temp times. And here again we're just changing the void p parameters pointer to the shared data. And this thing is just about the synchronization, which Matey is gonna cover it. And then again we just have the temperature interval, and here if all the driver went okay, it went not okay, something went wrong, then we are printing out that there's something wrong with the wake up method, and then we're putting some delay. And if something went wrong again with the measurement, then we are printing out that we can perform the measurement. Again, we're putting some delays because the humidity and temperature driver sensor needs some time to measure it. And then we're setting them up, the humidity and temperature, and then we're just printing out that the measurement is completed, and we're just printing some information what has been inserted into the shared data. So yeah, and pretty much all of the tasks works at the same concept, just like some of the tasks, like for instance CO2, during the initialization they have a callbacks, but we haven't used them, so we just basically initialized them and left them without the callbacks, and it works pretty fine without the usage of the callback. So yeah, and pretty much that's it. Just another thing that we need to initialize those tasks one by one, like asynchronous. So it should be temperature, CO2, light, and LoRa. Okay, and so right now Matey will talk about the synchronization.
Hey, Matej's here. I will say a few words about synchronization of tasks. It's achieved by using an event group. The event group works with bits, therefore we have a bit for every task. And the bits are defined here in the configuration defines header file. it can be seen that here we're defining the bits. What's interesting is the last bit, which is system ready. It is set or it's ready only when all other bits are set as well. The event group itself is included in the shared data struct, which we're using to save the different measurements, so temperature, CO2, humidity, and light. Let's go to a task. For example, the temperature humidity task. This is the body of our task. It has void as a return type, and as parameters it's taking void pointer. We change this pointer to our shared data struct, and afterwards we're setting the bits. This method takes an event group, so we give the event group of our shared data struct, and then we set the temperature humidity bit to be ready. Then we have another check. We're doing this by waiting for the bits. The event group is again the shared data. This time we are waiting for the system ready, because this secures that every task would reach this point, and after that it will successfully start measuring, or some sensors will need to wake up and then measure, like it's in this case. However, this system ready, it also needs to be checked second time, because there might be some tasks which haven't actually reached that part here. However, after that, as I said earlier, if this check is successful, they will just go down, and some sensors will need to wake up, like it's here. Others will start measuring. After that, we just use the shared data struct to set the temperature and the humidity. Now I give the word to my friend and colleague Haocheng.
Hi, Haocheng is here. Arduino board with shield. Sensor and the LoRa module is provided by via University College. We have 3 sensors for 4 different data, which is humidity and temperature, CO2 and the light. The driver was made by IP, and each measuring function is a task of FreeRTOS. If it is the first time running our program, you need to burn the code into the device. Now we connect it to the power cable and the debugger cable. Each term can print out the output message from the device. Let's run the code. Now the sensor have been initialized. Great, the LoRa connection is good to go. The device will send the data payload to the WebSocket every 5 minutes. Now the payload has been uploaded successfully. We can go to the WebSocket website to check it out. Few minutes later, we can receive some data from the device, which is at the top of the LoRa WebSocket website. We want to transmit floating point to the server, so each sensor data will occupy 4 bytes of the payload. Let's take first 8 hex digits as an example. I will put it into the converter. As you can see here, the temperature of the greenhouse is 22.4 Celsius. After this, data group will handle and process this data. They will tell you more about it.
So we have a connection to the IoT, which is shown here. The WebSocket client extends text web socket, and this is the URL to connect to the LoRaWAN network. So since this is our IoT endpoint, we get data from the LoRaWAN network and we send it to the database source. We have a helper class which helps us in converting the data that we get from the LoRaWAN network into the appropriate DTOs and entities. As you can see, we have DTOs here, which we take data transfer objects. So what happens in the WebSocket client is we get data from the LoRaWAN network using the handle text message method, and then we add it to the service class. The service is let me just go there. Payload service. Yeah. So the payload service is a service class which handles the logic for adding to the database this payload entity. So we have the payload repo, which is just basically a GPA repository which handles the entity and the ID here. So this is how we send data from the IoT into the LoRaWAN, into the data warehouse source, the source. We have a source model here, which is we're using the code first approach. So we generate the this into the database here in the applications.property, and we set this to create, but for now it's updates because we're updating. So then we have the Android endpoint where we have different controllers. It uses the controller class, Arturas controller, and then we use this path mapping to get data from our database. So we have the account controller, history controller to get the history where we have request parameters. We have light switch, which we try to get the state of the switch, and we perform some actions to the LoRaWAN network and some measurements to get the current measurement. So that is basically, we also have configuration files to handle every form of persistence or object relational mapping or anything like that. We also have the persistence.xml, which creates the data warehouse entities. Taking a look at our data warehouse, we have the source. The source here is named Postgres. We have data warehouse and the staging. So we can see here that this is some of the information we are getting from the LoRaWAN network, and we are receiving it here. So in our source, this is some of the information we get. We have, let me open the tables. Here we get some data from the LoRaWAN network. We get some device ID. There are no locations for now. This is not being handled by the LoRaWAN network. And in the payload, we basically get some payload values in accordance with the data and the device, which we send to our SEP, to the data warehouse. Yes, so as you can see here, the data warehouse is being filled up by using the triggers which we are using for change the CDC change data capture, which only handles inserting for the time being, and it also inserts into the device. So that is basically the whole structure, the system of our of the data team, data engineering, and I hope I have covered everything here. So thank you.
Project, or at least some of them. First of all, we didn't fully implement data capture changes. We are not covering deleting and updating changes. Therefore, the last updated table has no currently any use in our project. What's more, in the ER diagram of the staging, we wrote surrogate keys, which we all know is not true and it has no place in implementation in our project. Additionally, we've made mistake in the function which look up for the surrogate keys for the staging measurement from the data warehouse dimensions. Everything looks good except the condition which is using actually surrogate keys. So this, since this will be null because we look for it, the update will never trigger. So what's the solution? Solution is just to use device ID instead, because both of them have this at the same time rather than the device ID. During the project execution, we ran into problem with other subscription 2 times. Once during the project period in the really late stage, and second time after handing and before recording this presentation. What's more, we lost of our databases while losing subscription. Power BI was definitely not strong side of our project. We lack of data, that's why most likely some of the charts has really poor design. What's more, we are missing some charts which has better accuracy if it comes to single measurements, like the chart for only temperature, which would exactly show the right temperature with better accuracy. In the project report, we've mentioned something like measurement dimension, which doesn't exist. Of course, it's fact. Same with floating table, which has no use. Last update, we called it dimension. Pros and cons of our project. Definitely the good side is that we have object relational mapping, which simplify the maintenance between the model and database. We have almost close to real-time updates in data warehouse due to triggers. We believe our separation of concerns between logic, database and API is good. And we have loose coupling to object relational mapping framework thanks to Java Persistent API. So in the case we want to use something different, there is not much changes in the code. From the bad side, during the executions, there was no built-in scheduler in PostgreSQL like in other database servers. We wanted to use some external tool, but it was impossible to make it while hosting Postgres on Azure. What's more, there is quite high maintenance while having a connection to 2 different databases. Stop.
Welcome to SEP 4 Android presentation. In the design part, we made a class diagram, which is following process of a domain model, and here is demonstrated the architecture of the Android application and the structure of our programs in terms of classes, relations, attributes, and methods which we used. For instance, here you can see the relation between fragments, activities, and view models. Another thing what we made in the design part is a sequence diagram. And here is an example of sequence diagram from getting measurements data. So retrofit was implemented in getting measurements data. In the first marked point, the client interface sends get request type to database cloud as a measurement JSON object. In the second part, database cloud handles the get request and responds the measurement object to the client. In the third part, the callback get measurements from server will be executed when getting the response from the database cloud, and on failure will be called if there is a network failure. On response will be called if a response is handled from the database cloud. In the fourth part, the current data view model calls the get measurements from server from client repository. In the fifth part, measurement data will be bound with text view in layout, and measurement data will be displayed if no failure happens, if not, returning error. The next phase is testing, and the reason for several testing techniques was to test implemented functionalities continuously through the whole implementation process to catch invalid code as early as possible. We had two testing techniques. The first one is whitebox testing, where we use JUnit testing for specific components and classes. The second technique is blackbox testing, where we couldn't see the code and we had to test our GUI of the system. Here you can see our black box testing example, and that's a snippet of our full table. Every test case has an ID, which are defined in a way of easy filtering and tracking functional requirement status.
Hi, this is Junjia. The next part is implementation. There are four main theories used in our application: lab data, data bounding, room, and the recycle view.
Now let's see the code. The first thing is to declare dependency for them on Gradle. The first one I want to talk is lab data. Obviously, it's a basic tool to build this system. Lab data is an observable data holder that can observe the change of data stored in it, as shown on the screen. When the change of measurements happens, measurements lab data will invoke unchanged methods, and new measurements can be get from here. Then is data bounding, which is really a convenient tool to display values on the interface. Firstly, you need to implement data bounding layout and use label variable to define variable within label data. For bounding all these variables, you need to use this way here. Then change to the activity you want. Use data bounding util to initialize it. Next one is room. For saving setting of a lot of the temperature, humidity, and CO2. First step, create relate entity and DAO class. The entity presents one row in the table on the real database, and the DAO interface contains all circle statements need to be implemented. Then initialize room database, because the database will consume a lot of system resource. Use singleton here. Finally, use repository class to encapsulate them. Because of executor, the system can execute circle on background thread. The last one I want to talk is recycle view, which is used for show history in our system. First, create fragment history.xml to contain the recycle view component, and the item.xml to contain the layout of item will be shown on the recycle view. After this, because the data source comes from model measurements class, create a measurements adapter to handle the setting of the recycle view, which need to be extend a class recycleview.adapter. At least, create all instances of them in fragment history.
Here is Bowen. The second implementation is to show the details of display data. This part has 6 steps, and we will have a record for the details.
The first part of implementation
is to show the details of display the current data. The first step is client interface. The client interface to specify get measurements, and that is a get request. Also, location is used where the endpoint for the request is. The current is used to track API, and we can go to the second part, server generator. Yeah, we can write the local URL here to connect with the API. And we can go to the third step is client repository. Client repository is to perform the get request, which is created in client. The method is needed to do async with call queue, and it expects a callback. Measurements will be set value of the response. Live data is used to save the value of measurements. And we can go to the first step is view model. Get measurements multiple live data and get measurements from server calls from the client repository. And then we can go to the fifth step, current data fragment. Snipper is implemented here to choose which location to display measurements to data. We have two locations, front and the back. It calls the method get measurements from server with parameter location in view model to get the data from the server. Then we can go to the layout part, the last step. Data binding is implemented to bind text view and data directly in view model. After that, layout will display the data from API in text view. This part is to show how the application works. First, we start the database. Yeah, and we can go to Android Studio and start the application. We'll create an account, type Bowen and Bowen for password, and click sign up. Create was created. Account was created. We can go to the login. We click login. Yeah, we can log into the system. This part is to show the data, and the snipper is to let the user to choose which location you want to see. This is bank, and this is front. This part is to show history of the data. This part is to set alert. For example, we click the temperature, we type 10 to 15, and we click insert. Yeah, we can check the data here is too high. Let's check. Yeah, the system will to make a notification the temperature is too high. This is account. The system will give you a fake ID and your fake username. Yeah, that's all.
As you can see, we have 10 user stories completely implemented, 4 user stories partly implemented, and 1 user story which is not implemented at all. So the conclusion would be that 90% of the user stories were completely and partly implemented and passed the test. Android applications are able to retrieve data from IoT through the database, and of course, Android application is missing some of the parts to be functional, but most of these missing parts were filled with a dummy value, for instance, history and user profile.